Good morning. Are you able to hear me clearly? Can you hear me? Hello. Unanisikia? I cannot hear anyone, so I'm not sure whether you can hear me. So please, if you can hear me, confirm. Paul, Abubakar, can you hear me? Okay. And you can see my screen vizuri. Okay. Now I can hear you. Can you see my screen? I'm sharing a presentation, so please tell me if you can be able to see it. Paul, Abubakar, mnaona my screen?
No, the one for presentation is blank.
It's blank. You cannot see Malin imeandika plant, electrical and instrumentation, AC induction motors. Okay, let me try and present again. Are you able to see now? Mnaona sasa? Okay, today I'm not going to take a lot of time because I can see people are not watu sio wengi and I don't want to continue teaching class ambayo ni nusu. This topic is quite extensive and on Friday at least let people know that what okay. I know some people don't have access to smartphones ama laptop but angalau watu waingie ile Google Classroom because I am recording these classes and they can get the recordings of these classes there once I finish editing them. Abubakar, mnaweza ambia watu hata kama hataweza kuingia hii live class anaweza aingie ile nyingine tafadhali, kwa sababu hapo ndio mtapata notes, assignments, these materials that I used to teach zitakuwa hapo. Now, today I'm going to introduce the topic of induction motors. And to start us off, I'm just going to begin by explaining what an AC motor is. I'm sure every one of us tushaipatana na motor, hata ukiwa mtoto labda ulikuwa na ile toy ya gari ya motor. But those motors are DC motors. They use DC source, DC current to power the motor. But now an alternating motor is one that uses alternating sources. Yeah? I'm sure by now you already have an idea what DC and AC current and voltage is. Sindio? We have an idea what DC and AC current and voltage is. Yeah, so an AC motor is usually powered by an alternating current through electromagnetic induction. We will look at it in detail as we continue, but I want someone to explain to me what they think electromagnetic induction is. Anyone? Paul or Abubakar? I'm sure by now you have come across electromagnetic induction somewhere. What is electromagnetic induction? Paul? Electromagnetic induction ni nini?
That is like getting motion using the magnetic.
Yes. We will look at it in detail, but that is essentially what it is. We are going to make the rotor of that motor to rotate using the magnetic fields that are generated within the motor. Now, AC motors are usually classified into 4 major categories. Yeah? And the first one is the principle of operation. Sasa kulingana na how they operate, we can have either a synchronous motor or an induction motor. But this this topic sana we are going to be dealing with induction motors. But according to the principle of operation, we can have a synchronous motor and we can have an induction motor. Now, a synchronous motor, once it is connected to an AC source, a source that is varying in amplitude because of the supply frequency, we have now the once it is connected to an AC source, the magnetic field that is going to be generated will be rotating at something known as a synchronous speed. This is a term that we will come across a lot of times when we talk about motors, both especially AC motors. The magnetic field generated will be rotating within something known as air gap. There's no point of writing air gap, but the magnetic field will be rotating at something known as synchronous speed within the air gap. The air gap is the space between the rotor and something known as a stator. We will look at these components as we move forward, but a synchronous speed we rotate at, a synchronous motor we rotate at synchronous speed. The magnetic field will rotate at that speed, and the rotor the rotor ambayo itakuwa connected to the mechanical shaft will also be rotating at synchronous speed. But since you're not talking about synchronous motors, we'll just briefly pass through it briefly too. Now, this is a diagrammatic representation that shows how a synchronous motor usually is. We have the rotor, the pole. You have the poles of a rotor and you have the poles of the stator. I don't know if you understand when I say stator and rotor. Mnaelewa namaanisha nini? Do you understand when I say stator and rotor? Do you understand what I am saying? Are we together? Because I don't know if you can hear me. Hello? Abubakar? Okay. Now, as I was saying, I was asking, do you understand when I say stator and rotor, tofauti ni nini? Mnaelewa tofauti ni nini ama tu mnanyamaza? Let me show you a pic. Nasikia mtu akielezea tofauti, so if you can tell me please, niambie sahi tofauti ya stator na rotor ni nini?
I think the rotor is that
Yes, the rotor is the rotating part, and it is usually connected to the shaft. And the stator is that stationary part within that motor. We will look at we will look at them in detail during the constructional features of the AC motors. But a synchronous motor, what happens is once you connect AC supply to the stator, the AC supply is usually connected to the stator. It will generate a rotating magnetic field which will be rotating at synchronous speed. The rotating magnetic field generated by the stator will be rotating at synchronous speed, and in this example synchronous speed is 3600 revolutions per minute. Now at t is equals to 0, the pole pairs of, this is a pole pair north south of the stator, zitakuwa at that position. The pole pairs of rotor will be at that position. Now what happens? The rotating magnetic field will interact with the rotor. Now at this point, what am I saying? the pole. The pole pairs of the rotor will be attracted to those of the stator. So as the magnetic field of the stator rotates, it will rotate haraka. Once let's look at these two what's going on kidogo tu. Now once this the EMF generated, the rotating magnetic field will rotate quickly. The stator, it rotates sana. So you'll find that once this, for example, in this case, this magnetic field will rotate too fast, and it has, in this case, it has made a half a revolution. The north pole itakuja chini and the south pole itakuja chini, but the rotor will still have haitakuwa imesonga because of high inertia. Initial high inertia will be too high. So what happens is when this rotating magnetic field of the stator rotates, the rotor will have barely moved. So what happens is the rotor tends to vibrate in position, because what happens is at this point the attraction between the pole pairs will make the rotor to start rotating in the direction of the magnetic field. But since the stator magnetic field will be rotating at a high speed, and because of the initial inertia of the rotor, utapata kwamba that the rotor, the stator magnetic field, itakuwa imemake maybe a complete revolution. In this case, itakuwa imemake it has made a half revolution at t is equals to t1, but the rotor has not moved. So what happens is the rotation of the rotor will try to, the poles will start rotating in the opposite direction. Lakini the stator will again rotate faster. So you'll find that the rotor will just be vibrating, pulsating at a fixed position. So asynchronous. So this means that asynchronous is not self-starting. So you have to provide additional mechanisms to ensure that ianze, to make it self-starting. So that is just basically a asynchronous motor. We're not going to talk about it in detail. I was just trying to show how the working principle of a synchronous motor. But what I wanted to really explain is that a synchronous motor will be operating at synchronous speeds. It is constant. The speed of the rotor will be constant. So once you how you make it self-starting is you can provide additional windings on the rotor, known as amateur or damper windings, or you can I don't want to explain. Do you want me to explain how a synchronous motor is made self-starting? It is not part of our syllabus, but I can just explain in briefly.
Yes, I can explain.
Okay. Now, as I was saying that the rotor will be pulsating hapo tu, because the synchronous speed of the magnetic field generated by the stator will be too fast for the rotor. So when the north pole and the south pole at this point, so the rotor will be attracted by the magnetic field of the stator. So itajaribu kuifollow, but now the stator magnetic field will move too fast. So itafika at this now before even the rotor begins to move, itakuwa isharudia the starting point. So what will happen? It will try to rotate in the opposite direction, but again the stator field will move too fast because the rotor has high inertia, high starting inertia. So how we make this self-starting? Number one, we can have supply frequency. We can supply the stator, the AC that is being supplied to the stator. We can vary the supply. We can start at low. We can start supplying it kidogo, so that when the speed, so that we can limit the speed. The speed of a motor. I don't know if we can. Let me switch kidogo to. Tell me if you're able to see my screen vizuri. You can see what I'm writing. ama iko blur?
Haionekani vizuri.
So what can I do? Let's see. Shida ni internet na kuna shida ya network kidogo, but let us see.
Yeah. 120F over.
Yes, you can see that.
Yes.
Now this N represents the speed of the rotating magnetic field, and it is given by 120 times the frequency of supply divided by the pole pairs, the number of poles in that motor. So what happens to the speed of motor once you decrease the frequency? When you decrease the frequency of supply, if you're supplying pole, the speed itapungua. So if I'm supplying the AC at 50 hertz, and if I'm supplying AC at 20 hertz, you'll see that the 50 hertz, the speed will be high. The 20 hertz supply will be lower. So how we can make a synchronous motor self-starting is by first supplying it at a lower frequency, so that the speed inakuwa ndogo. So once let's see, you can see the presentation now. I think you can see the presentation. Now, once you supply the speed kidogo, what will happen is since the rotating magnetic field of the stator will be at a lower speed, the rotor poles will be able to lock. Hazitaachwa nyuma, so they'll be able to lock. So once these poles of the stator and the rotor lock, then you can increase the frequency of supply. So once you increase the frequency of supply, what happens is that the speed of the motor increases until it reaches the maximum speed, which is known as the synchronous speed. So you can make and that is how you make the one way of making the synchronous motor self-starting. Another way is by starting it as an induction motor. So what happens is you provide additional windings known as damper windings, but we won't talk about that now. Let us continue with what we are doing today, which is induction motors. But based on principle of operation, we can have synchronous motor or induction motor. Now, what is an induction motor? The basis of an induction motor is that you will have electromagnetic induction happening. This is once you supply AC current into the stator windings, we have a magnetic field which is produced. Now this magnetic field induces current in the rotor because the rotor of the rotor circuit is usually shorted. So a current is usually produced. Once a current is produced, this rotor also generates its magnetic field. So the magnetic field of the rotor and the magnetic field of the stator link, flux linkage. So once they link, then they will be rotating in the same field, in the same direction. So the magnetic field of the rotor will link with that of the stator, and then it will follow the direction. The rotation of the rotor will follow the direction of the rotation of the magnetic field produced by the stator. So that is just the basic meaning of how the basic principle of how an induction motor works. Now, classification according to current. The supply current into the AC current can be single phase or it can be three phase. Paul, I remember during our last physical class, I had asked you to go find out the difference between between single phase and three phase. Nikakwambia the next time we meet when utatuelezea tofauti. So what is the difference between single phase and three phase?
Single phase is supplied in like in 3 core wires, in 3 different wires.
Single phase ama 3-phase?
See, 3 phase has got 3 live wires,
Yeah.
and single phase has got 1 live wire.
Yes. Essentially, it just depends on the type of application, but single phase will have 1 phase wire and a neutral. And 3-phase will have 3 phase wires and a neutral and earthing. All of them will have earthing. So now we can classify then our AC motors as single phase or 3-phase depending with the type of supply. Now, depending on the speed of operation, we can classify AC motors as variable speed, constant speed, or adjustable speed. For variable speed and adjustable speed, depending on the speed that we want, we can be able to vary. AC motors mfano kama ile ambayo inapatikana katika blender ambazo ziko nyumbani, you are able to vary the speed of that motor. So depending on the application of the motor, then the speed can be varied or it can be constant. You can have a constant speed. Mfano katika hizi pumps ambazo zinatumika to discharge cargo in ships, those are usually variable speed. The pumps ambazo zinatumika in compressors, those are constant speed because you want to supply air into these reservoirs at constant speed. So depending on the speed of operation, we can have variable speed ama constant speed. We have classification according to structural features. The stator can be open. No, the motor can be open. It can be semi-enclosed. It can be enclosed. It can be ventilated, depending on where you're applying these motors. When you're using these motors in places that you're doing or you're having flammable materials, your motor will be enclosed. The stator itakuwa imefunikwa. The motor will have an outer covering, a stator frame. Now we together. But this is just the basic motors, the basic structural features. It can be open, it can be semi-enclosed, it can be enclosed, it can be ventilated, it can be pipe ventilated. You can go look at the differences later on. Unaweza enda uangalia picha ukaona tofauti ni nini, but depending on the application, then we can have the stator ama the motor ama the frame either open, semi-enclosed, enclosed, ventilated and the like. Are we together until that point?
Yes.
Now, when we talk about single-phase motors, we can classify single-phase motors as single-phase induction motors. We can have single-phase synchronous motors, and we can have single-phase series motors. I told you as an assignment for last week, since we didn't meet last week, that you will go and find out these single-phase synchronous motors and single-phase series motors, where they are used, how they are used, how they look like, tofauti ni gani. And we've just talked briefly about synchronous motors kidogo tu, that they rotate at synchronous speed, at constant speed. It doesn't change. Now today, for me, I'll be talking about single-phase induction motors. Hii nimewaachia as an assignment ama as a presentation. You can go make short notes, you can go make a presentation, and then when we meet as all of us, we'll share what you learned about single-phase synchronous motors, single-phase series motors. Single-phase series motors can be powered by AC or DC. Zinakuwa powered by AC or DC. Synchronous motors ni hizo nimekuambia. When the AC is supplied to the stator, then the rotor and the magnetic field produced by the stator rotate at the same speed, known as synchronous speed. Now let us look at induction motors, single-phase induction motors. I will play a very short clip, and then we will discuss in detail as we move forward.
If you find this video interesting, then please like and share it. Also, leave your comments below.
Are you able to hear? Mnaweza sikia? Hello? Okay.
The construction of the single-phase motors
Let me start that video again.
If you find this video interesting, then please like and share it. Also, leave your comments below. Don't forget to subscribe to our channel and click on the bell icon for notifications.
Let's study the single-phase induction motors. They are mainly used in fans, mixers, washing machines, etc. The construction of the single-phase motors is very similar to the three-phase motor, with the stator made up of multiple sheets of laminated steel. The slots are provided on the inside perimeter on which the coil is mounted. Being the single-phase motor, it has distributed single-phase winding. The rotor construction is squirrel cage type. Thus, the copper bars are permanently shorted at both the ends with the help of 3 springs. When the single-phase AC supply is connected to the rotor, a magnetic flux is generated which rotates along the axis only. It never rotates like a 3-phase motor. Hence, single-phase motors are not self-starting. To overcome this problem, auxiliary winding is added to it temporarily 90 degrees apart from the main winding, making it a 2-phase motor. Thus, once the 2-phase motor is supplied with single-phase AC supply, the rotating flux is generated. When these magnetic field lines are cut by the rotor lines, the conductor current. This current produces in the rotor, and the torque is generated and drives the motor. A centrifugal switch is connected in series with the auxiliary winding and is located inside the motor. Once the motor reaches the speed of 70 to 80% of synchronous speed, the starting auxiliary winding is disconnected from the supply with the help of the switch. There are 3 types of single-phase motors depending on the type of winding used: split-phase motor, capacitor start motor, and shaded pole induction motor. There must be large phase difference between the currents of auxiliary winding and main winding of the motor needs to act as a 2-phase motor.
If you find this video interesting,
Now, I don't know if you've been able to hear what has been said, but I will just explain briefly. Not briefly, I mean, I'll explain pole pole. But I want to change my screen so that what you see is what I'm writing. I don't know whether it will be clear. I'm hoping it will be. Now, single phase. Are you able to see visual, Paul?
Anaiona vizuri.
Okay. Now, when we talk about, nitakuwa naandika hivi, so nikiandika hivi inamaanisha single phase. Single phase induction motors. When I write like that, I just mean single phase induction motors. Now, single phase induction motors, tumeambiwa that their construction are similar to 3-phase motors, 3-phase induction motors, but because we haven't looked at 3-phase induction motors, we will just talk about the general construction of a single phase, and a 3-phase. Now, these motors consist of a stator and a rotor. They consist of a stator and a rotor. And we have been told that the stator is usually made up, no, the rotor is made up of laminated high-grade sheet steel, When we say laminated, we kumaanisha that there are very many pieces that have been put together. And the reason why we do this, we laminate our rotor, is to reduce eddy currents, and we reduce magnetism, locking of magnetism between the stator and the rotor. The lamination is very important because it reduces the eddy currents produced by the magnetism, and we prevent the locking of the magnetic circuit of the stator and the rotor. Now, the rotor is made of that, and then we've seen that the slots of the rotor are inside of the slots are inside, hizi hapa ziko ndani ya the rotor. The stator contains windings. In this case we're talking about of single phase. The stator ambayo iko nje iko na one phase. Something I want to introduce again, a new term is distributed winding. and I want you to go find out the difference between distributed winding and concentrated winding. Tofauti ni gani? Because we're going to be mentioning the word distributed sana sana. So what is the difference between distributed and concentrated? But now we are talking about distributed. Distributed has its advantages because it provides a smoother waveform. A waveform here, distributed winding of the AC, the AC circuit is smoother. So it will. That means that the motor, the AC motor, will be running at quieter. It will be smoother and it will be quieter. Now, as we know that the rotor is usually connected within. I mean, the rotor is within the stator. Now we've seen that in the single phase motor, the single phase rotor. Tumeambia that it is not self-starting. I don't know if you heard that part katika hiyo video. We've been told that it is not self-starting, and I'm going to explain this using something known as double revolving field theory. Double revolving field theory. Why is it not self-starting? Because the motor is being supplied using single phase supply. Let me draw this diagram, this schematic diagram, so that we can understand what I mean. So we have a single phase supply, and we have the distributed winding that is on the stator. This is the stator and this is the rotor. The rotor, we have the stator and we have the rotor. Now, once the AC supply is connected, once the stator is supplied with single phase supply, this rotor doesn't have any rotating torque. The rotor doesn't have any rotating starting torque. Why doesn't that motor, the rotor, begin moving? This is because there's something that we will see. The behavior of single phase supply, the magnetic field that is produced by a single phase supply is pulsating. We will see why the motor doesn't have any starting torque. But once you give this rotor a push, you can rotate it manually, or you can have other connections that will help it to start. So once you rotate it manually, or you connect it using other external connection, then it can be able to rotate. But initially, once you, especially, let us explain it when ikiwa imesimama, when it is not moving. The single phase supply will produce a pulsating flux, a pulsating magnetic field. Now, I've said I'm going to explain this using something known as double revolving field. Now, what happens is, if you look at that diagram I've drawn, we have the single phase supply, and we have the distributed winding. Now, now we are talking about when the rotor is at standstill. The rotor has not been manually moved. The rotor is not moving. The rotor is at standstill. Now we are talking about the operation of single phase induction motor. So once you supply AC into this stator, a flux, a pulsating flux, is usually produced. Let me give it that. So a pulsating flux is produced, and this pulsating flux is along the same axis of the stator winding, the distributed stator winding. Now this is just the rotor. So this pulsating flux will induce current. It will induce current into this rotor, because we are talking about electromagnetic induction. So the rotor, this pulsating flux that is being produced by the stator will induce current in this rotor. The rotor, that current will produce its own flux, which I'll give it, I'll label it as phi r. Flux is usually ndio symbol ya flux. The number of lines produced, zile lines ambazo zinakuwa produced by a magnetic source are known as flux. So the induced current in the rotor circuit will produce its own flux, which I've labeled as phi r, which is pulsating along the same axis as this one. So zitakuwa along the same axis. Now there's a law, because we're talking about electromagnetic induction, there are laws that govern this phenomenon. We have Faraday's law of electromagnetic induction. This I want you to go find out, and Lenz's law. Now Lenz's law is what we are talking about here in this case. Once the stator flux and the rotor flux are produced, these fluxes will tend to oppose each other, and this is Lenz's law. Once a flux is produced, it will tend to oppose the force that has produced it. Lenz's law of electromagnetic induction. Go look at these two laws and tell me the difference. We'll see, because these laws zitakuwa mentioned a lot in terms of electromagnetism. So this is what happens when the rotor is at standstill. We'll have a flux being produced when the AC single phase supply is connected to the stator. That flux will induce will induce current in the rotor circuit. That current will also produce a pulsating stator flux, a pulsating rotor flux, which will tend to oppose the stator flux producing it. And this is, I've said, this is governed by Lenz's law. This is the rotor at standstill. The rotor is constant. Now, when the rotor is moving, and we have said that we can cause the rotor to move mechanically, you can take the shaft ya hiyo rotor ukaizungusha na mkono. Now, when the rotor is running, and you have said you can produce the movement of the rotor by hand, or you can connect auxiliary circuits. You can connect auxiliary circuits to enable the rotation of the rotor. Now, what the double field? I don't know if I've written the double field revolving theory. Iko namna hii. This phi, hii phi ambayo inakuwa produced, this flux produced by the single phase supply, which is connected to the stator, can be visioned, and it can be seen to be two equal. So let me draw this. This flux phi can be seen to be two equal rotating fields. Now let us see this mathematically. Wacha tuingie mambo ya vectors. Since an AC supply is a vector quantity, and when I say a vector quantity, I mean that it is a quantity that has both magnitude and direction. Now, let us look at this in this case. Let us consider two vectors. I'll label them OP and OP. This vector is rotating in the anti-clockwise direction at an angular speed omega s, and this vector OP is rotating in the opposite clockwise direction with the angular velocity omega p. Now the vector sum, when you add those two vectors, you'll find that the sum of these two vectors will be twice this. Are we together? I'm just explaining this analytically so that we can see why, the operation. We had started with the operation of the rotor, the operation of the single phase induction motor when the rotor is standstill haisongi. Tukasema that a flux is produced by the single phase supply on the stator. That single phase supply will induce current in the rotor circuit, and that current will produce a pulsating flux. These fluxes will tend to oppose each other because of this law, ambayo nimesema Lenz's law. Now we are looking at the rotor while it is rotating, and this can be done by hand. You can take the shaft of the rotor, you can twist. Okay? Once you twist it, it will rotate. Ama you can have auxiliary circuits which will aid in the rotation of the circuit. Now what I'm trying to explain in this case is how this rotor will start. Ama how it will develop that torque that will enable it to rotate. Now, let us imagine two vectors, OP. This vector is rotating in the anticlockwise direction with angular velocity omega s, and we have this rotating in the angular direction, in the clockwise direction, having angular velocity omega s. The vector sum of this is twice. This is this value of, that is, let me label it OR, will be twice OP. Are we together? I don't know if we are together. Kama nawapoteza ulizeni maswali tafadhali. Okay. Now, these vectors are representing the flux OS. This flux is rotating. These two vectors are rotating at the same speed, but in opposite directions. They are rotating at the same speed but in opposite directions. Sawa. Now the vector sum OR will be twice OP, and it is lying on the same line, the same axis as hizi zingine. Now when this as this vectors zikirotate, let's say this is rotating like that, this is rotating like that, this is OP, this is OP, this ina rotate hivi at omega s, this ina rotate at omega s. When you look at this vector sum, utaona ina reduce in size. As this rotates, at that point, this will be 0. This is OP. This vector sum will be 0. As it continues to rotate, as these vectors continue to rotate, this vector sum will increase in value but in the opposite direction. Mpaka mahali itafika. When these vectors have rotated in the opposite direction, and the vector sum will be twice. Will be twice those two individual vectors, but you will see, as you can see the difference. This will be, let's say, upright, now this will be itakuwa ina face chini, but they're in the same, they are along the same axis. Now, this is just mathematically speaking. Now, this we can do this, but in the sense of that flux being produced by the AC supply, the single phase AC supply. Therefore, this OR is representing that state of flux ambayo inakuwa generated. I don't know if I've drawn that. This OR, this vector sum OR is representing this state of flux being produced by the single phase supply. And this state of flux can therefore be seen as having two rotating fields, which are rotating at the same speed but at different directions. So once this pulsating field OS is the equivalent of these two these two rotating fields. I don't know if I've explained that vizuri. Naona ni kama nimepotea kidogo. Nimeexplain vizuri ama mimi ndio naona? Sijui kama nimeexplain vizuri. Paul, are we together?
Kwa vector sum tumeona vizuri, lakini sasa vector direction.
Now, what I was saying, mathematically speaking, when you have two vectors, and they are rotating they have the same speed and they are rotating in the opposite directions. When you add them, zitakuwa namna hii. Are we together? There will be this vector sum, in this case OR, will be along the same axis. Kama sahi in this position, let's say this is at time t is equals to t1. The sum of these two, OP plus OP, itakuwa 2OP. They will be in the same direction, and the value of the vector sum will be twice these vectors. Once this vector starts rotating, now they are rotating in different directions. This vector sum itakuwa inapungua because this angle is increasing. So this value itakuwa inapungua mpaka mahali itafika these vectors zitakuwa zina face in this direction. When these vectors are facing in this direction, then this place, the vector sum will be 0 because they are equal in magnitude. Will be 0. Give me a minute. Nipatie dakika moja tu. Hola. Okay.
Abubakar, mineta tunatusikwa.
Hebu kidogo, mnaweza nipatia dakika 5 narudi sasa hivi?
Sawa sawa. Abubakar. Network ilikuwa kusumbua. Tupati vizuri. Ni network sindio? Poa basi. Sawa. Mimi napata kiasi. Sasa upati gani? Upati hiyo huku kwa vectors. Ama kwa synchronous. Lakini vectors inaeleweka. Unaongea na Mike kweli? Unaongea na Mike hivi karibuni? Hujaongea na Mike?
I don't know if you can hear me now. Can you hear me?
Yes.
I was explaining how we resolve the rotating magnetic field, the pulsating flux produced by the stator, as two rotating magnetic fields that are rotating in the opposite direction. Now nikasema, mathematically speaking, when you have, can you see my screen?
Yes.
Okay. Mathematically speaking, when you have a vector, this vector tukaipatia, we have two vectors. These two vectors, OP and OP, are rotating in the opposite direction, but they are rotating at the same speed. This sum, the sum of these vectors, the vector sum, can be represented as OR. And at this position, the vector sum itakuwa along the same axis. And it will be twice that value. Now, as these vectors rotate, this angle between them will increase. As this angle increases, utapata kwamba the vector sum value itakuwa inapungua. Itapungua mpaka mahali when these vectors are at that position, the vector sum will be 0. Zikiendelea rotate and they are rotating now, you'll find that this value of the vector sum itakuwa inapungua. Itakuwa inaongezeka, but in the opposite direction. Up to that point where it will reach that these vectors zimerotate. They have completely rotated, and you'll find that this vector sum of these two rotating vectors itakuwa twice their value, but now in the opposite direction. Sawa. Now what I wanted to now this vector sum hii ambayo tumekuwa tukiangalia hapa is similar to this pulsating. We can take this vector sum to be the pulsating flux produced by the single phase AC supply on the stator. So once this flux, we can represent the single phase, the flux produced by the single phase. This means that this flux, if this OP, 2OP, is the flux produced by the stator, in kumaanisha kwamba that this flux can be represented as two. This flux can be represented as two fluxes, two rotating fields that are rotating at the same speed, but in different directions. Are you together? This is what I was trying to show. That mathematically speaking, you have vectors, but now this sum vector, can represent our flux. This vector represents our flux, and this flux can be written, can be proven that it is two rotating fields that are rotating at the same speed but in different directions. Hapo tumeelewa?
Hapo iko sawa.
Okay. Now, what happens? Since we have seen that the pulsating flux, pulsating ni kama heartbeat, pulse, inakuja inapotea. So in this case, unapata that inapanda inashuka. So now we have seen that this pulsating flux can be resolved as two rotating fluxes that are rotating at the same speed but in different directions. Now these fluxes usually generate an effect. Since now you have a pulsating flux, and this flux to honor that it is, we have seen that it can be resolved into two rotating fluxes. So we'll have, now let me represent this as, this is the flux rotating in the forward direction, and this is the flux rotating in the backward direction. Now the force ambayo inakuwa produced by the stator, the force that is being produced by the stator can be represented mathematically as Ni times cos theta. This is the force that we're just, this formula I'm just showing you. The force that is being the magnetic force that is being produced by the stator can be represented by this, where N is the number of turns. I is the instantaneous current. The current at that particular point, instantaneous current. The current at that certain angle theta. We have seen that when these vectors are rotating, there is an angle being formed. So the current at that particular angle is I, small I, the instantaneous current. So that force that is being produced by the flux, the stator flux will be given as N, I cos theta. Now let I, this is the equation, the equation of a sinusoidal value. Kama ingekuwa voltage ingekuwa V, but now we are talking about current because we are talking about supply current. Now let I equal to I max times cos omega t. Cos omega t is the angle that the current will have rotated, ama itakuwa imemove with respect to time. Remember, this is a sinusoidal wave. Now this is the general equation of a sinusoidal wave. In this case, since you're talking about current, that I max need the maximum, the amplitude, the value at the maximum, the peak value. Now, the force being produced by the forward, itakuwa Ni max all over 2 cos omega t minus theta plus Ni max over 2 cos I'm sorry. Cos omega t. You'll never be told to derive these formulas. I'm just trying to explain why. I'm just trying to explain the forces that are produced, the effect of having two fluxes. We are resolving the stator flux as having two fluxes. Now, what is that effect? What effect is generated by resolving the flux as two fluxes? Now, what I've done is I've taken this formula up here, force. We are analyzing this mathematically now, analytically. So the force being generated by the flux is given by the number of turns times the current cos theta. Now, the forward, the force at a particular angle, at a particular time, will be given by N I max cos omega times cos omega t. What I've done is I've taken this formula ambayo tumepatia hapa of the force being produced by flux, and you see that we have seen that the instantaneous current is given by the maximum. Abubakar, please mute kidogo tu. Now, I was saying that the current I will be given by I max times cos omega t. So what you've done here, ndio tupata hii hapa, we have taken this value of I, the instantaneous current, and then we have replaced it here katika hii formula, na tukapata that F at a particular angle, the force being generated by the electromagnetic induction by the flux produced is that. Once we resolve this, tukiendelea ku resolve easy mathematically, you'll find that the force, the rotating flux, the force produced by the rotating flux is the sum of the force produced by the rotating field in the forward direction plus the force produced by the rotating field in the opposite, the backward direction. These forces, these individual forces, produce induction motor torque. They produce torque. These forces produce torque, but this torque is being produced in opposite directions. Now, when I draw the torque speed characteristics of this motor, of an induction motor, a single phase induction motor, you'll see that the torque being produced by the forward rotating field. These are formulas, you don't have to pay much attention to them. What I was really interested in is this part. I wanted to explain this part, but nimeona if I start deriving the formulas then tunaweza potea kidogo. So let us just know that the resultant force being generated by the pulsating flux, which is produced by the supply, the single phase AC supply, is a component of the force being produced by the forward rotating field plus the force being produced by the backward rotating field. These forces generate something known as they generate torque, induction torque, but these torques are rotating in opposite directions. Now, when you draw the torque speed characteristics of this induction motor, you'll find that the torque, this is torque, and this is speed. The torque being produced by the forward revolving field itakuwa ni kitu kama hiyo, and the torque being produced by the backward revolving field is something like that. Now, the resultant torque, when you add those two torques together, you get something like that. So you have a resultant, the torque at the torque at that is being produced by the forward revolving field, and the torque being produced by the backward. This is a backward field, and this is the resultant torque. When you add these two torques, unapata hiyo. Now, I want you to note something. When this motor is at standstill, the value of the forward revolving field and the value of the backward revolving field are the same. We had mentioned that this motor is not self-starting. The reason is, once you supply single phase AC supply, the pulsating flux, ile value ambayo this pulsating flux produced by the AC supply, tumeona that it can be resolved as two rotating fields that are rotating but in opposite directions. And hapa, these rotating fields will produce force, and this force will induce torque in the motor. But now, when this motor imesimama, the rotor is not rotating, that forward field and that backward field, the torque produced from those two fields will be equal, and they will cancel out. So the magnitude will be 0. The magnitude of that torque will be 0. So that means that the rotor will not rotate. But once you now rotate the rotor, once you rotate the rotor, the rotor starts moving, and you have said the rotor can move by hand, you can connect auxiliary circuits. You'll find that, for example, if I rotate that torque, that motor in the clockwise the forward direction, you'll find that the resultant torque will the direction of that motor, it will take the direction in which the rotor has been rotated. So in this case, look at now the resultant torque in the forward direction. When you add this forward field, because now the motor is rotating, the rotor is rotating in the forward direction. We've enabled the rotor to rotate in the forward direction. So what happens is the two torques are now unequal. The forward torque will be higher than the backward torque, and that this torque, the forward torque, the resultant torque, will keep the motor rotating in this direction. If you rotate the rotor and it is rotating in this direction, these two torques will be unequal. So the direction of rotation will now be in this opposite direction. Are we together? Paul, tuko sawa? Ama naongea peke yangu?
Yeah. Tuko sawa.
Now we are seeing why this motor is not self-starting.
Yes.
Are we having an idea why it's not self-starting and how we can make it self-starting? I know it's very difficult to understand mara ya kwanza, but what I can do is I can recommend some videos which can explain simpler. My explanation might not be the most simple, but I just want you to understand if you're given kwa mtihani and you're told to explain double revolving theory, you are able to. Now, I don't know if you have seen this. Now, let us talk about something known as sleep. This is an induction motor, and it operates na kitu ambayo tunaita sleep. This is the difference between the speed, the synchronous speed ns of the magnetic field produced by the stator and the speed of the rotor. These two speeds will not be rotating at the same speed, because this is not a synchronous motor. This is an induction motor, and an induction motor works under that the synchronous speed will be rotating at a higher speed than the rotor speed. The synchronous speed is the speed at which the magnetic field produced by the stator will be rotating at the air gap. The air gap nilisema that it is the space between the rotor and the stator. Now, assuming that the rotor is rotating in the forward direction, the difference, the slip in the forward direction will be given by ns, the speed of the rotating field produced by the single phase supply, the rotating field stator, minus the rotating speed rotor, divided by the synchronous speed. And this can just be indicated by S. The slip of forward. The slip of forward. If the motor is rotating in the forward direction, the slip will be given by ns minus n over ns. Now, when you look at the slip with respect to the backward direction, itakuwa ns minus n. The reason being that the motor will be rotating in the opposite direction. That's why you're giving the negative value, divided by ns. This is the same as ns plus n over ns. Sawa. Now, this ns hapa tunaweza sema that it is 2ns minus ns. Sindio? 2ns minus ns gives you ns. Mathematically speaking, come I have 1, I can say that 1 is 2 minus 1. What we are doing is that we want to expand this slip so that we can get it in a value that iko na es. Let me just continue so that you can see what I mean. Now this ns can be represented as 2ns minus ns. Tuendelee na hiyo formula, plus ns over ns. Now since these values, the numerator share a common denominator, hii ni kama kusema 2ns over ns minus ns minus over ns plus ns over ns. Now, the final formula ya slip in the backward direction will be 2 minus s. This is the slip with respect to the backward direction. This is what I just wanted to show you, that we can get slip, we can represent slip in the forward direction as s, we can represent slip in the backward direction as 2 minus s. Now, these fluxes, we have seen that the fluxes, the stator flux, can be resolved as two fluxes that are rotating at the same speed but in different direction. Now, what is the effect of these fluxes on the rotor circuit? Remember that this rotor circuit there is a current being induced in that rotor circuit. So what happens is that you will find that we'll have, it's like you have two rotors, because you have a flux that is inducing current in the forward direction, and you have flux inducing current in the backward direction, and you have slip in the backward direction, and you have slip in the forward direction. So essentially is this flux, when it's resolved as a backward and a forward flux, in combination in our rotor as well, kutakuwa na effect ya forward na effect ya backward flux. Now, if we represent this effect as a circuit, we'll have a circuit we'll have a circuit. Now this is the rotor. The circuit of a rotor, when it is represented in the forward, and it is being represented in the forward, when the effect, or the effect of the flux is in the forward direction. Now remember, it is a rotor. We have the effect of resistance because of the wire, and the effect of inductance because it is a coil. Remember that a rotor is usually made up of coils, the motor itself. So kutakuwa na ile aspect ya resistance kwa sababu ya resistance of movement of current in that wire, and we have the aspect of inductance because the wire imekuwa coiled. Now when you represent that rotor, the rotor circuit, because of the forward flux, itakuwa namna hii. We have an induced voltage in that circuit. We have the current that is being produced by the forward flux. We have the inductance labeled as X subscript 2. Now we have the resistance, which is R2 divided by the slip. The same, we have a circuit, the effect of the backward flux can be represented in form of a circuit. We have the current being produced. We have the inductance, which in this case inaitwa inductive reactance. Inductive reactance. We have the resistance. But now the resistance of the backward, because of the backward flux, the flux rotating the backward direction, itakuwa namna hiyo. It will be the resistance value divided by 2 minus S, the slip. Remember, because these circuits are being based upon the stator, the flux, the stator flux. And then this, we have the voltage being induced, but now in the backward direction, by the backward flux. Now, what I wanted to introduce today is that topic. Naona time yangu inaenda sana and I have another class right now. But my biggest concern today was my biggest aim today was introducing AC motors. Hii mambo ya hizi circuits, we'll continue with them next class because we have some calculations that we need to do. Are we together, Paul, and the rest? Ama ni wewe tumebaki?
Yes, we are together.
Okay. Now, I hope you've...
So that is
yes?
on Friday.
Yes, on Friday. We'll meet on that class and tell the people to attend. What they can do for this week until that point is they can watch videos, they can catch up on how an induction motor, a single phase induction motor works. So that when you come to the next class, kile tutafanya ni tutaanza na calculations as we look at how these backward and forward fluxes affect the rotor. Sawa sawa?
Okay.